discuss about unity step function and second shifting theorem. The unity step function is denoted by u of t minus a or u a of t, and it is defined by u a of t equal to 0 when t less than a and equal to 1 when t greater than a, where a greater than or equal to 0 is fixed. The unity step function is also called a Heaviside function. Now the figure is like this. The unity step function u of t minus a is like this. When t less than a, it takes the value 0, and when t greater than a, it takes the value 1. Okay. Now let us move to the second shifting theorem. The statement is like this. Here, if L of f of t equal to f of s, then L of f of t minus a u of t minus a is equal to e raised to minus as f of s. This is our second shifting theorem. We can consider the proof also. First, we can consider the formula of L of f of t. That is, we know integral L of f of t equal to integral from 0 to infinity e raised to minus st f of t dt. Okay. Now, instead of f of t, here we can consider f of t minus a, u of t minus a. Okay. Therefore, L of f of t minus a, u of t minus a is equal to integral from 0 to infinity e raised to minus st f of t minus a into u of t minus a dt. Now here u of t minus a is our unity step function. Now in order to apply its values, we can split this integral like this. At first, the integral is from 0 to a e raised to minus st f of t minus a u of t minus a dt. Now the second one is a to infinity e raised to minus st f of t minus a u of t minus a dt. Now we can apply the function values here. Okay. Now that is equal to, now when t less than a, the function value is 0. So u of t minus a becomes 0. This reduces to 0 and here this value reduces to 1. So the first integral becomes 0. So this is equal to integral from a to infinity e raised to minus st f of t minus a dt. Now here we can use one substitution. Put t minus a is equal to u. Okay. So we have t equal to a plus u. And also what is dt? dt equal to du. Okay. So when t equal to a, what is u when t equal to a? Here you have u equal to a minus a. Okay, so u become 0. And when t equal to infinity, u become infinity minus a. That means infinity. So here u varies from 0 to infinity. So here this is integral from 0 to infinity e raised to minus s. Now instead of t you can write a plus u. Then instead of f of t minus a you can write f of u. Then dt means du. Now this is equal to integral from 0 to infinity e raised to minus as e raised to minus su f of u du. Now here e raised to minus as is independent of u, so you can take it outside. So that is e raised to minus as into integral from 0 to infinity e raised to minus su f of u du. Okay, now here we have this one. This term represent our L of f of t or L of f of u. So this is equal to e raised to minus as into L of f of u. Okay. So this is same as e raised to minus as into f of s. Okay. So this is the second shifting theorem. Now from the second shifting theorem we can move to one corollary now. That is, the corollary says L, here we have by second shifting theorem we have L of f of t minus a into u of t minus a is equal to e raised to minus as into f of s. Now we can take this L to the other side. Okay, therefore what is L inverse of e raised to minus as into f of s? This is same as f of t minus a into u of t minus a. Okay, this is corollary to the second shifting theorem. Now we can find the Laplace transform of the unit step function. That means we have to find what is L of t minus a. The answer is e raised to minus as divided by s, where s is positive. Now here we have L of f of t. We can consider the proof now. L of f of t is integral from 0 to infinity e raised to minus st f of t dt. Now instead of f of t, here we can consider our unit step function u of t minus a. So this is integral from 0 to infinity e raised to minus st u of t minus a dt. Here also we can split the integrals like this. Integral from 0 to a e raised to minus st. Then when t less than a, the value of u of t minus a is 0. So 0 dt plus integral from a to infinity e raised to minus st. Then the function value here is 1. So 1 into dt. So the first integral reduces to 0. Now there remains integral a to infinity e raised to minus st dt only. Now what is integral e raised to minus st? That is e raised to minus st divided by minus s, and here t varying from a to infinity. Now we can substitute the upper and lower limit here. So that is equal to at first we can consider that minus 1 by s outside, then e raised to minus infinity minus e raised to minus as. Okay, so this is minus 1 by s. E raised to minus infinity is 0. So e raised to minus as. So this is equal to e raised to minus as divided by s. So this is the Laplace transform of the unit step function. Okay. Now we can move to a problem now. The question is like this. Find L inverse e raised to minus 3s divided by s cube. Now, this question is of the form L inverse of e raised to minus as into f of s. Okay. Now, when comparing these two, we can see that f of s equal to 1 by s cube. What is f of s? F of s means L of f of t. Okay. Now, from this, you can find f of t. What is f of t now? F of t is L inverse of 1 by s cube. Okay. And what is L inverse 1 by s cube? That is t square divided by 2 factorial. That means t square by 2. Now, we can consider the formula of L inverse of e raised to minus as into f of s. Now, this is equal to, by corollary to the second shifting theorem, that is equal to f of t minus a into u of t minus a. Okay, so L inverse of e raised to minus 3s into 1 by s cube is equal to, what is our f of t? T square by 2. So instead of t, you have to consider t minus a. What is the value of a here? A is equal to 3. Okay, in this problem, here a is equal to 3. So here we have a f of t minus 3. F of t minus 3 into u of t minus 3. Now we can substitute the values here. F of t is t square by 2. So here we have t minus 3 the whole square divided by 2 factorial into u of t minus 3. Okay. Now you can substitute the value of u of t minus 3 here. So this is equal to t minus 3 the whole square divided by 2 factorial into 1 when t greater than or equal to 3. And it takes the value 0. That means t minus 3 whole square by 2 factorial into 0 when t less than 3. Okay. So this is the required answer here. Now we can move to another problem now. Second question. Find L inverse e raised to minus 3s divided by s minus 1 whole power 4. Okay. Now here also we can consider this question to L inverse of e raised to minus as into f of s. Okay. Now when comparing, you can see that a is equal to 3 and f of s is equal to 1 by s minus 1 whole power 4. So what is f of t? So f of t is L inverse of 1 by s minus 1 whole power 4. And this is equal to t cube divided by 3 factorial. 3 factorial means 6. Then into e raised to t. Okay. This is our f of t now. Now we have the formula L inverse of e raised to minus as into f of s equal to f of t minus a into u of t minus a. Therefore, L inverse of e raised to minus 3s divided by s minus 1 whole power 4 is equal to f of t minus 3 into u of t minus 3. And f of t minus 3 is t minus 3 the whole cube divided by 6 into e raised to t minus 3, and you can substitute the value of u of t minus 3 also. Okay. We know u of t minus 3 takes the value 0 when t less than 3 and equal to 1 when t greater than or equal to 3. Okay. So, you have the function value is t minus 3 the whole raised to 3 by 6 into e raised to t minus 3 into 1. That is when t greater than 3. And takes the value 0 when t less than or equal to 3. Okay. So, this is our required answer. Now, again, we can consider one more problem now. The next question is like this. Solve the initial value problem. D square y by dt square plus 2y equal to r of t. Here y of 0 is 0 and y dash 0 is 0. And where r of t is given, r of t is takes the value 1 when t greater than or equal to 1 and 0 when t less than 1. Okay. Now when seeing this r of t, you can see that this is our unit step function u of t minus 1 or u1 of t, ua of t. That means u1 of t. Here a is equal to 1. Okay. Now the given question is y double dash plus 2y is equal to r of t. Now here r of t is our unit step function. Now we can take the Laplace transform on both sides. So L of y double dash plus 2 into L of y equal to L of r of t. R of t is the unit step function u of t minus 1. Okay. Now what is L of y double dash? The formula is s square into y of s minus s into y of 0 minus y dash of 0. Apply that formula. And here plus 2 into L of y. L of y is y of s. And here the Laplace transform of the unit step function is e raised to minus as by s. So here we have e raised to minus a is 1. So e raised to minus s divided by s. Now you can substitute the value of y of 0 as 0, y dash 0 as 0. So there remains s square plus 2 into y of s equal to e raised to minus s divided by s. Okay, from that we can calculate our y of s. So y of s is equal to e raised to minus s divided by s into s square plus 2. Okay. Now here we can apply the method of partial fraction. So here we have 1 by s into s square plus 2. So this is equal to a by s plus b by s square. Here s square plus 2. Okay, this is not a linear term. So here we have to consider bs plus c. Now taking the LCM, you can see that 1 is equal to a into s square plus 2 plus bs plus c into s. Now compare the coefficient of s square on both sides. So you have a plus b equal to 0. And next compare the coefficient of s. So here the coefficient of s is c only. So c equal to 0. Then coefficient of constant. That means 2a. 2a is equal to 1. From this we have a equal to 1 by 2. So b equal to minus 1 by 2 and c is 0. So here we have y of s is equal to e raised to minus s. Then we have a by s. A is 1 by 2. So 1 by 2 by s plus c is 0. So bs. B is minus 1 by 2. Minus 1 by 2 s divided by s square plus 2. So this is our partial fraction. Okay. Now this is equal to, here we have 1 by 2 is constant. So we can take that constant outside. So e raised to minus s divided by 2. Then 1 by s minus s by s square plus 2. So y of s means L of y of t. Okay. So from this we can calculate our y of t now. Therefore y of t is given by y of t is taking L inverse. So we have 1 by 2 into L inverse e raised to minus s by s. 1 by 2 is common. Then minus L inverse e raised to minus s by s square plus 2. Okay. Now we have that is equal to 1 by 2. Then L inverse of e raised to minus s by s is our Laplace transform of the unit step function u of t minus 1. So this is u of t minus 1. Then minus L inverse of e raised to minus s by s square plus root 2 square. Okay, so we have s by, so that function related to our cos. Then here e raised to minus as into f of s model. So the corollary to the second shifting theorem. So we have that is equal to f of t minus 1 into u of t minus 1. Now our f is cos function. So we have cos root 2 t minus 1 into u of t minus 1. Okay. So this is of the form. Listen. Here we can see that here this function is of the form L inverse of e raised to minus as into f of s model. corollary to the second shifting theorem, and its answer is f of t minus a into u of t minus a. Here e raised to minus as, so a is 1. Okay, here a is 1, and f of s is s by s square plus 2. So here its corresponding f of t is cos function. So s by, so cos at, that is cos root 2t. Okay, that is our f of t. So here we have f of t minus a. So root 2 into t minus 1, u of t minus 1. So this is our required answer. 1 by 2 into u of t minus 1 minus cos root 2 t minus 1 u of t minus 1. Here u of t minus 1 is also common. So if you want, you can take it outside. So the answer is 1 by 2 into 1 minus cos root 2 t minus 1. Then into u of t minus 1. Okay. So this is our required answer. Okay. Now let us stop here. Thank you all.